So something I want to do to review the previous video, normally what I would have you do is I'd split you up into 4 groups and I would send you back to a lab station. And at your lab station, you would have one of these 4 blocks. And the first question I would ask you is to identify what element your block represents. And then I would ask you to tell me how many atoms are in your block. So since you aren't able to do that, I'll go ahead and tell you the answers to that activity. So what you would do is you'd take one of these blocks and you'd notice that it says 1 mole. And you would put it on the scale, put it on your balance and see how much it weighs. And then you would look on your periodic table and see if the weight, if the mass of this block matched anything on the periodic table. And then you'd be able to identify what element it is. For the question about how many atoms are in the block, the fact that this is 1 mole means that each of these contains 6.022 times 10 to the 23rd atoms. So notice they're different sizes. If you could hold them, you'd be able to tell that some are lighter or heavier than the others, and that's just because each element has a different molar mass based on the numbers of protons and neutrons in that element. So just to give you an example, you can probably tell that this one is copper just based on the color of it. But if you took this block and put it on the balance, it would weigh 63.55 grams. And that's because you have 1 mole of copper, the molar mass would be 63.55. And then it has 6.022 times 10 to the 23rd atoms in this block because this is 1 mole of copper. The second thing I wanted to show you is the poster that I keep on my whiteboard. This poster is all about moles, but I'm focusing on one part of the poster, and this is just to give you an idea of how big Avogadro's number really is. So imagine you have a mole of $1 bills. So you have 6.022 times 10 to the 23rd dollars. And if you were spending that money at a rate of $1 billion per second, how long do you think it would take? And normally when I ask this question, students just off the top of their head are like, oh, you know, probably take 10 years. And I keep saying, nope, it's higher than that, it's higher than that. No one expects it to be as high as it really is, which is 19 million years. So it would take millions of lifetimes to spend that amount of money, even if you were spending it at a rate of $1 billion per second. So it's difficult to comprehend a number this large, but I felt like this was a pretty good illustration of that. So we're going to return to our PowerPoint, and in the previous lesson we talked about molar mass, we talked about percent composition. Now in this video, I'm going to teach you how to do mole conversions. And for this, you're just going to have to use dimensional analysis and the flow chart if needed. And you're probably wondering, what is the flow chart? I will show you that in just a minute. But you'll notice on the next few slides, I've got several questions we're going to answer together. And we're just going to do those on a separate sheet of paper on my document camera. So I'll switch over to that now. So starting with this very first problem, the question is how many grams of argon are in 0.652 moles of argon? So hopefully you remember how we set up dimensional analysis problems. You always start with what you know. So I know how many moles I have of argon. What I don't know is how many grams that is equal to. So starting with what I know, I have 0.652 moles of argon. By the way, I don't know if I've mentioned this, but the abbreviation for mole is just MOL, leaving the E off. So I know that really saves us a lot of time. All right, so continuing on with this problem, we're going to move moles down to the bottom to cancel it out. We're going to put what we don't know, which is grams, on top. So you might notice that we've set up our problem grams per mole. So we're going to be plugging in the molar mass for argon. So looking at our periodic table, argon's mass is 39.95. And I'm going to put that next to grams, because remember, that's how many grams there are in 1 mole of argon. So now you can see all I need to do is multiply across. So I'm going to type in 0.652 times 39.95, and I get 26 grams of argon as my answer. All right, moving on to our second problem, well, sixth problem in this PowerPoint, but second of the mole conversions problem. We're supposed to find the moles of sulfuric acid that are equal to 139.7 grams of sulfuric acid. So we know how many grams we have. We don't know how many moles. So let's start with what we know, 139.7 grams. I'm going to cancel grams out by moving it to the bottom and put moles on top. So now you might notice, once again, it's grams per mole. It's just reversed. So I will be plugging in my molar mass next to grams, and I'm going to be putting 1 next to mole, grams per 1 mole. So I need to calculate the molar mass of sulfuric acid. Well, hopefully you remember how to write formulas for acids. If it ends in ick, then we're talking about sulfate. I ate something icky. So that's SO4. SO4 has a -2 charge, so we need 2 hydrogens in front of it. So now I'm going to list out each element. 2 hydrogens, 1 sulfur, 4 oxygens, and I'm going to multiply by their molar masses. So again, looking at our periodic table, hydrogen's molar mass is 1.01. Sulfur's molar mass is 32.06. Oxygen's molar mass is 16. So I'm going to multiply each of those and add them together. So 2.02 plus 32.06 plus 64. And you get 98.08 grams per mole. And we're going to be putting that next to grams. So you might notice we are dividing here. 139.7 times 1 divided by 98.08. And we get 1.42 moles of sulfuric acid. All right, moving on to our next problem. For number 7, we are trying to find the number of molecules in 4.4 moles of barium chloride. So we know we have 4.4 moles. We don't know how many molecules we have. So starting with what we know, I'm going to move moles to the bottom, molecules goes on top. And notice we're not using anything with grams. So you're not going to be plugging in the molar mass like we did before. So you need to ask yourself, how many molecules are in a mole? How many of anything is in a mole? That's where we're going to plug in Avogadro's number. And I know on my original slide, it only said 6.02. I normally go 6.022 when I do my problems. All right, so notice for all of these problems, we're always, for our conversion factor, talking about how many grams are in a mole or how many particles are in a mole. So notice for each of the problems we've done so far, you put 1 next to mole. If you're using the molar mass, that goes next to grams. 1 is next to mole, 1 is next to mole. And if you're talking about atoms or molecules, you're going to be putting Avogadro's number next to that. So we're going to multiply these two numbers. And I want to show you my calculator screen because it's been a little bit since we've typed things in using scientific notation. So that's 4.4 times 6.022. This is where you use your E button. So you don't need to press times or times something to the whatever power. You just press that E button and then 23. So I can round. This is going to be 2.6 times 10 to the 24th is my answer. And notice we didn't even need to know barium chloride's formula. You really only need to know that for molar mass and for a different type of problem I'll be showing you later. But when all you're doing is using Avogadro's number, we didn't really need to know this formula. All right, moving on to number 8. How many moles of nitrogen dioxide are in 5.34 times 10 to the 14th molecules? So we know how many molecules we have this time. We don't know how many moles. So start with what you know. 5.34 times 10 to the 14th molecules. Move molecules to the bottom. Moles goes on top because that's what we're solving for. Remember that 1 goes next to mole and Avogadro's number is going to go next to molecules. So this time we are dividing. We're taking this number times 1 divided by Avogadro's number. So 5.34 E14 divided by 6.022 E23. I get 8.87 times 10 to the negative 10. And that is moles of nitrogen dioxide.